Hello, and welcome to this lesson on predicting the products of electrolysis for aqueous ionic compounds. In today's lesson, we will firstly explain how to predict the products of electrolysis for aqueous ionic compounds based on the reactivity series. We will also understand the significance of water molecules in the process of electrolysis. So far, you have successfully familiarized yourself with electrolysis of molten ionic substances. You've learned that when an ionic compound is melted, it breaks down into its constituent ions, which can then move freely to the electrodes, where reduction and oxidation occur. Building on this foundation, we will now explore the electrolysis process with the extra consideration of water added in. Let's dive into the main body of our lesson and learn how to predict the products of electrolysis of aqueous solutions. The process for identifying products for aqueous solutions is quite similar to the process outlined in the previous lesson on molten ionic compounds. The one difference is that you need to remember the existence of water molecules. Firstly, we must determine the ions present in the aqueous ionic compound. When an ionic compound is dissolved in water, it splits into its constituent ions. For instance, if we have sodium chloride in water, it dissociates into sodium ions and chloride ions. However, those are not the only ions present, as we need to consider water molecules. Water molecules can dissociate to form hydrogen ions and hydroxide ions. So, in this case, we have sodium ions, chlorine ions, hydrogen ions, and hydroxide ions in the solution. The next step is to determine the electrode reactions. Firstly, at the cathode, which is the negative electrode, the positive ions are attracted to the cathode. Reduction occurs at the cathode, meaning the cations will gain electrons. To predict which ion gets reduced, we use the reactivity series. The reactivity series lists metals in order of their reactivity, starting with the most reactive. If the metal cation is more reactive than hydrogen, like the sodium plus ion in our example, the hydrogen ions will be reduced instead, forming hydrogen gas. The reduction reaction would be 2H plus 2E- becomes gaseous H2. If the metal cation is less reactive than hydrogen, so for example, if we had silver ions, the metal ion will be reduced, depositing as a solid metal. The reduction reaction would be Ag plus E- becomes solid Ag. Now looking at the anode, which is the positive electrode, the negative ions are attracted to the anode. Oxidation occurs at the anode, meaning the anions will lose electrons. To predict which ion gets oxidized, we consider the type of anion. If the anion is a halide, like chloride, bromide or iodide, the halide ion will be oxidized to form its respective halogen gas. For example, chloride ions will form chlorine gas. If it is not a halide ion, like nitrate or sulfate, the hydroxide ions, OH- from water will be oxidized instead, forming oxygen gas and water. The oxidation reaction would be 4OH- becomes gaseous O2, plus 2H2O plus 4E-. The final step is to identify the products. The final products of electrolysis are the elements or compounds formed at the electrodes. Using our earlier example of NaCl in water, at the cathode hydrogen gas, H2, would be produced because Na+ is more reactive than H+. At the anode, chlorine gas, Cl2, would be produced because Cl- is a halide ion. We can confirm our predictions of products by carrying out tests. These tests will be covered again in the chemical analysis unit, but for reference, here are the tests for a few chemicals that are commonly produced in electrolysis. To test for hydrogen gas, expose the produced gas to a lit splint. A squeaky pop sound being heard confirms the presence of hydrogen. To test for oxygen gas, expose the produced gas to a glowing splint. If the splint relights, then oxygen gas is present. If bromine gas is released, it will be visually observed as a red-brown gas. Similarly, chlorine is a yellow-green gas. This can be confirmed by exposing the produced gas to damp blue litmus paper. Presence of chlorine gas is confirmed if the litmus paper turns red and then bleaches to white. Let's dive into some GCSE level questions. Here is our first question. Pause here to have a go. Now for the answer. First, determine the ions present. In aqueous copper sulfate, we have Cu2+, SO4, 2-, H+, and OH- ions. At the cathode, Cu2+ and H+ ions are attracted to the cathode. Using the reactivity series, we see that copper is less reactive than hydrogen. Therefore, Cu2+ ions will be reduced, depositing as solid copper, Cu. The reduction reaction is Cu2 plus 2E minus becomes Cu, solid. At the anode, sulfate and hydroxide ions are attracted to the anode. Sulfate is not a halide, so hydroxide ions will be oxidized instead. The oxidation reaction is 4OH minus becomes gaseous, O2 plus 2H2O plus 4E minus. Thus, the products of the electrolysis of aqueous copper sulfate are copper deposited at the cathode and oxygen gas released at the anode. Now, for our next question, predict the products of the electrolysis of aqueous potassium iodide. You may want to pause here to have a go. Now for the answer. First, determine the ions present. In aqueous Ki, we have K+, I-, H+, and OH- ions. At the cathode, K+ and H+ ions are attracted to the cathode. Potassium is more reactive than hydrogen. Therefore, H+ ions will be reduced to hydrogen gas. The reduction reaction is 2H+ plus 2E- becomes gaseous H2. At the anode, iodide and hydroxide ions are attracted to the anode. Iodide is a halide, so it will be oxidized. The oxidation reaction is 2I- becomes solid I2 plus 2E-. Therefore, the products of the electrolysis of aqueous potassium iodide are hydrogen gas at the cathode and iodine at the anode. Now, for our final question, predict the products of the electrolysis of aqueous sodium nitrate. You may want to pause here to have a go. Now for the answer. First, determine the ions present. In aqueous NaNO3, we have Na+, NO3-, H+, and OH- ions. At the cathode, Na+ and H+ ions are attracted to the cathode. Sodium is more reactive than hydrogen. Therefore, H+ ions will be reduced to hydrogen gas. The reduction reaction is 2H+ plus 2E- becomes gaseous H2. At the anode, nitrate and hydroxide ions are attracted to the anode. Nitrate is not a halide, so hydroxide ions will be oxidized. The oxidation reaction is 4OH- becomes gaseous O2 plus 2H2O plus 4E-. Thus, the products of the electrolysis of aqueous NaNO3 are hydrogen gas at the cathode and oxygen gas at the anode. These examples illustrate the process of predicting the products of electrolysis for various aqueous ionic compounds. By identifying the ions present, determining the electrode reactions based on reactivity and anion type, and knowing the standard electrode equations, you can systematically predict the outcomes of electrolysis. In today's lesson, we delved into predicting the products of electrolysis for aqueous ionic compounds by understanding the roles of the reactivity series and the principles of reduction and oxidation at the electrodes, considering the presence of water molecules. By following a systematic approach, this lesson has equipped us with the knowledge to predict the products of electrolysis for any aqueous ionic compound, a vital skill in real-world chemistry. Next, we examine the reactions occurring at each electrode. At the cathode, cations undergo reduction by gaining electrons to form neutral atoms or molecules, whereas at the anode, anions undergo oxidation by losing electrons to form neutral atoms or molecules. We then applied this understanding to numerous specific examples, sharpening our understanding. You are now equipped with a solid understanding of electrolysis of molten ionic compounds.